No. You can't do multiple comparisons. You can't say mild but not moderate. That doesn't make sense. You can't do that after the fact. Oh, shit. Which one of these worked? Let's point to this one. This one's the good one. You got to understand how fraudulent that is. Like, that's just not how statistics in medicine is done. I can't say, you know what it's like saying? It's like saying, okay, here's a coin flip. I'm going to do 10 coin flips. Let's do it just for your benefit, all right? Ran between 0 and 1, okay? And let's see, I'm going to count these flips, 86 flips, right? And I'm just going to copy and paste just so I have it. 86 flips, right? And I say, well, who is mild and who is moderate? Let's do flips for that. Look how easy this is. Look how easy this is to fraud. You're gonna laugh. Nah, dude, it's not possible, John. I'm sorry. And I'll explain why in a second. I'm not just gonna give you short shrift. I'll explain. And we can get on the phone. We can go on Discord if you want. And again, I'm a polite person. I'm not some crazy guy. Be happy to be polite with you. Okay, so this is the code for mild, moderate. Mild is 0, moderate is 1. This is the code for worked or didn't work. Let's just kind of simplify it for that. Worked would be, let's see, didn't work is 0, and worked is 1. So there's 86 patients. We have raw data here. And we're just going to see what the average is. So the average did not work. The average was literally very close to 0.1, very close to 0.5. But because of random chance, it was actually slightly on the side of what? Not working. Okay? But one of these two groups did better than the other. And I don't know which is which, but let's go find out. Let's data sort by C. And I'll give you another subgroup here. I'm going to do ApoE, Apo. So this is ApoE4. This is the bad gene for Alzheimer's. And this is ApoE3 or 2. This is the good gene for Alzheimer's. I'm going to do one more. Hold on. Let me see here. Okay, I got it. All right, that's fine. For now, that's fine. So let's see what the average was for the mild guys. So we're going to sort by, no headers, the sort by cell C, column C. And yeah, that's fine. Okay. So in our fake experiment here, there's 41 mild patients, and they did were closer to, they did better than the moderate. Tell you something. And our fake moderate patients, there were slightly more of those, and they did worse. But both missed statistical significance. And now if we sort by ApoE and disregard mild or moderate, well, if you got the bad ApoE, you did really bad. And if you got the good ApoE, you did really good. Damn, it's the only one we have that's at 50%. So both the data are bad. I'm on discord.gg/Martin Shkreli. If you use Discord, or you can send you a phone number. 2 Kanye coupons left for Godel, by the way. Use keyword or code word coupon free code Kanye, Kanye, capital letters, and you get 50% off Godel for a month. Let's see here. Here is the other Discord invite. So yeah, I'm in the Discord Everyone Can Speak channel. So if you come in, happy to have a cordial conversation. But again, here you have like, these are just made up data. And, you know, you have the data for this. Now, if we go even crazier, we can do 8scog. So let's try that. 8scog, and I'll just do equals rand between, I don't know, let's look at the data they actually got. We'll see if we can simulate it. ADASCOG. Get your mind out of the toilet. Okay, so here's their 8scog change from baseline. It was sort of randomly assigned between 7 and -12. So basically 0 to 20 is the spread. So we could just do rand between 0 to 20, and you could adjust that baseline for, you can add 5 basically to it. So you get, let me see here, we just say multiply it by -1 and then add 5. Right, so the worst scores, the best score you can get is 5. Right, and let's see if that's right. Min -15, that's the worst score you can get, and max is 5. That's right. Okay, good formula there. Yeah, John, we're waiting for you. Okay, mild, moderate, we assign randomly. ApoE, we assign randomly. So now let's see what this looks like. All right, I'm going to freeze these. So this is patient ID. Say 1. Just add them up. Okay. Now I'm going to paste these. This is a really good experiment. Okay, first things first, we're just going to, oh, well, we also have to assign placebo or drug, right? So say placebo, 1 for drugs, 0, and then 1 for drug. So the first, what, 43, 42, 43? How many are there? 86, so that's 43. And the next are drug. Okay. This is fun. All right, so now we're going to see, okay, what is the average? Okay, placebo, 8scog. Placebo 8scog is -5.8. That's pretty familiar, isn't it? And the drug 8scog, I just thought of an even better way to do this, but drug 8scog is, wow, -4.8. It's a point better. That's actually better than Kasafa did. Just by random chance. Literally. Just by random chance. It's a point better. Do my eyes deceive me? Let's see here. Average. Yeah, that's crazy. So right there, we get an Alzheimer's drug. Sort of shows you how stupid it is, right? But the problem is this would not hit stat sig. Why not? Well, what's the standard deviation? Six, which is about what we expect it to be, by the way. And the standard deviation is 6 here too. It just happened to be the distribution. What do you think the ITT 8S cog was? And we can agree that in this trial, there's no effect. It's just a random number. But the average is 5.3. And this is the key thing here. Yeah, it's a pen and paper test, something like that. It's also like, look at the ceiling, look at the floor, who's the president today? Like there's a bunch of stuff like that. And here's the point. Here's the 8S cog that we simulated with this random number, right? And there is a group, this is 5.3, but here's a group that did 4.8. And it happened to be the group we assigned to drug, just randomly. I didn't sit there and look at it. And then there was a group that we assigned to placebo, again, happened to be random. This could have been the other way around. That was 5.8. Was there an effect? No. It's because you're picking these two lines that separate from the mean. They're both equal distant from the mean. And here's the thing. There are infinite groups that you can define that have some delta from the mean. This delta is not cabined by anything other than your imagination. How many subgroups can you define? Mild, moderate, ApoE, MMSE, what would you pick your pick? So how about drug versus placebo and just mild? Let's do, oh, I kind of, all right, let's just do just mild. Okay. Mild and placebo. Oh man, they did terrible. Mild and drug. Let's see how those guys did. Yeah, I may have messed this up a little. Oh no, there's the group. Mild and drug. That would be 1 and 1, right? Okay. Average 6.4. So in this situation, it actually didn't work so great for milds, but moderates, you know, there's an effect in moderates because it has to be the same delta separation. So because we know we got a separation here, we have to have a separation somewhere here. The separation is not clear here. The effect size here is really small, right? Just 0.29. So the effect size here should be maybe massive. Let's add it up. So on placebo, these guys were negative 485. Quite good. But on drug, and again, you could define it as lower is better or higher is better. So in this case, we're doing lower is better, but we could easily define it the other way around. So it doesn't really matter which direction we define it in. But so for moderate is 1. We're kind of mixing up here. So let's start again. Mild is 0, okay, and placebo is 0. So these guys are negative. So mild and placebo, did we do it right the first time? They're 6.69. Okay, good. All right, that we got right. There's only four of these, right? So then there's mild and drug. And those guys we got it. Oh, 2.66. So huge difference in milds, right? Almost, probably statistically significant, right? We could even put that in. We could actually put that in. Oh, this is hilarious. I hope you guys understand how stupid and funny this is. This is why we care about stat sig. And I have a p-value simulator on my GitHub if you really want to dig into it. Well, phase 3, the FDA checks. And it's all independent doctors reporting their data. So you're not going to get that kind of collusion. But you're right. They could take that data and throw it away and say, oh, too bad. All right. So what will GraphPad tell us is the p-value here? This is going to be hilarious, dude. All right. So GraphPad says we got semifilam. We got placebo. The mean here change is negative 2.66, negative 6.70, standard deviation 5.904, 6.12, and 23, and 18. Calculate now, stat sig. P-value equals 0.0387. But I'm doing a multiple comparisons, and I'm not adjusting for multiple comparisons. Multiple comparisons is a very important thing. If you only can use P05 here. P05 has to happen here. If it doesn't happen here, you can't say, well, this is P05. No, this at best has to be less than like 0.001 because of the Bonferrari error correction or multiple comparison correction. Very important concept. You cannot just take infinite multiple comparisons without a penalty. Bonferrari. I don't know where I'm saying that. Bonferroni error correction. Bonferrari was the car guy. So anyway, on moderate, which is 1, and placebo, which is 0. Okay. And then moderate and drug, which is 1 and 1. You also had a separation, but not as good. And this would not be stat sig. Okay, why did I do this? Well, you can define, here's another, I actually like to show you, just to be clear here, one last thing. I want to count how many people were on placebo, which is 0. Let me sort by that at least. All right, C, smallest to largest, okay. I think we set it to 43, so that should be, yeah, okay, it's 43 each. But now I'm going to use GraphPad to see if this would have been stat sig. So in this case, semifilam was 0.483721, and remember, in the real world, it was not stat sig. So the fact that even a random coin flip would beat them is a little suspect, but all right, 43, 43. I say this won't be stat sig, but maybe it will be. Yeah, see, p-value here is 0.4501. You report this, Wall Street tells you failed, right? What a disaster. P-value 0.45? You know it has to be less than 0.05. But we found a subgroup, the same subgroup Kasava found. We just found a subgroup by accident that narrowly hits that p-value. 0.0387. How about the other subgroup? Would that have hit? Well, in this subgroup, you get the opposite effect, right? In one of these, placebo is a lot better. In one of these, the drug's a lot better. So the reason I did this is I want to show you what happens when you do this and you do it for a huge study. So how big is this new study? How big is this new study? Anybody know how many patients it is? I put it in my p-value calculator, of course, but I don't remember off the top of my head. 804. Okay. They didn't get lucky with their trials. They failed their trials. They found a subgroup that worked, and it's easy to find a subgroup that works, is my point. You know, looking really quickly again at the, let's look at the Lilly or the, either the donanemab or lecanemab will help us here, but this is super easy to tell. We basically say there's mild and moderate, APO4 carrier or non-carrier. If you do race or sex, I think you just get laughed at because we know that that's probably not going to be relevant. Oh, amyloid burden. High amyloid burden or low amyloid burden. That's a good one. And you could even do severity by different scores. So again, they had on all the patients, which I don't even believe they're telling us all the patients, but on all the patients, they had a 0.6 change, which is worse than our random number generator, which is funny. But let's do an 800 patient study randomly. And what you're going to find, I'll spoil it for you, is that once you add more patients, all the bullshit goes away. The subgroups don't work anymore by random chance. If you make enough subgroups, they might work by random chance, but this will not happen in a large study. And that's why this study is going to fail. It's just simple statistics. Okay, so we got 804 patients. We're going to do this really carefully. I'm going to copy the ADAS-COG formula because that was really good. And we're going to define once and for all that, how they defined it, which is, in this case, just the numbers. A big negative score is improving, and a positive score is declining. So once again, negative score, higher, negative is better, positive is worse. Okay, so we'll do that last. Right now I want to do placebo or drug. Okay, so average, no, because ran between 0 and 1. And then I'm going to do mild and moderate. So mild is 0. I'm going to predefine that here. And moderate is 1. Okay, mild, moderate. ApoE, bad is 0, good is 1. And then what was the new subgroup? Amyloid burden I made up. Amyloid burden. 0 is low, 1 is high. Is central limit theorem. Sounds familiar. Okay. And then we're going to, let's assign these guys right now so there's no bias. And you can see, just with common sense, that the more patients we have, the less likely you're going to get a random good luck subgroup. What are you doing with 80 patients? It's not hard. It just came up right away for us. All right, so now let's do, well, I removed this formula, so I have to remember this formula. It was equals, well, let me do it again up here. Equals ran between 0 and 20. So this is like the amount of ADAS-COG changes. I do think they knew this stuff. And then we're going to multiply by -1 to get it reversed. And we're going to add 5. Okay, yeah, that's what worked. All right, so now we do the ADAS-COG changes. And then I'm going to copy and paste the values just to freeze it, because otherwise it'll recalculate it each time. Now, if it is like I think it is, the drug doesn't do anything. It doesn't hurt or help. Then what I think will happen, let's see, Sava simulation, I'll call this. What I think will happen is the ADAS-COG change will be roughly the same between the two groups. Let's see if I'm right. I'm sweating a little bit, even though this isn't even the real thing. I'm sweating a little bit. Okay, we do have headers in this case, so let's go Placebo drug? Okay. Placebo patients. And they are going to get some kind of data like this. I don't know if it'll be in Excel, but they're going to get something like this. Okay, placebo is negative 4.81. And if we just look at Excel, we hover over or select over all of these 400 or something patients. Yeah, 4.81. 16. All right. And now we have simifilam. I'll start from the bottom. Go up until I get to the average, or last one. And the average here, okay, that's a sum. The average, -5. Same number practically. Notice how much smaller the delta got. It was 1 point up here. It got smaller here, only 0.2. What's the standard deviation? Six. What's the standard deviation for this guy? And you could do something called Monte Carlo simulation. You could run the simulation 1,000 times. And the same thing will happen over and over and over again. How many people? Let's see. I think we set this up to be exactly even, right? No, we set this randomly, which is more realistic. Okay, and the p-value? Let's do the exact calculator. Simifilam was -5. What did we say? Lower is better? The higher the negative number, the better. So simifilam was a tiny bit better. Not enough for approval. Why? Well, it's a very small amount. And then here's the real killer, the stat sig. Is this going to be statistically significant? The answer is no. But how bad is it going to be? P-value 0.6678. So they're basically saying it's highly likely that this was due to chance. And that's true. So we used a random number generator. But now let's go fishing for subgroups. And let's see how hard or easy this is going to be. Because you know they're going to try to do this. You know they're scumbags, right? They're going to try to do this. So let's look for this first subgroup as mild. Okay, so mild placebo. And again, I think it's random. And I did random, and you showed the big difference here. But let's see if the difference, you can detect any difference in this. And we have a lot more patients. So the subgroups are bigger. So the statistics takes over again. And the law of large numbers, somebody said central limit theorem, sort of gets in the way. So let's see what happens. And again, I would encourage you to do your own simulations. Some of you are stronger in math. Some of you are weaker. Programming, same thing. Try it. This is just pen and paper. Okay, so you have a subgroup effect here. Notice how it's the delta here, right, is 0.2. The delta here is 0.8. Well, 0.8 is almost good enough, right? Well, let's see. And you can see kind of like, you can kind of contrive these, like, even with random numbers, you could pretend, oh yeah, it works. This is not what a good drug looks like. And obviously, because this is literally a sugar pill. Which sugar pill is better? Now, again, because we missed the p-value here, we really can't do a statistical analysis here. So even if you do get something like this, it doesn't count. And that's what I think a lot of the longs don't understand. You can't do it because you're constantly searching for that needle in the haystack, and it's just not a real thing. Oh, Wes is here? Hey, Wes.
Hey, how goes it?
Good, how are you?
Doing all right.
All right, so I'm just finishing this little demonstration, and then we could chit chat about the whole thing, because this is only a small part of it. But on this fake subgroup we generated,
And you didn't exclude any here, right? Like
I didn't throw anything out.
Exclusions.
Yeah, you can throw some
From the
out.
trial data set.
In this case, the p-value missed as well. So even though there was a nice little separation, the p-value couldn't quite make it, although with a smaller amount, perhaps you could make it. So, and that's interesting, right? The p-value here was better because the size difference was better. But once you start with the law of large numbers, if the drug isn't really good, they all kind of blend in and you lose everything. So the drug has to have this big like separation, 2, 3, 4 points of ADAS-Cog. Otherwise, it's not going to look great in phase 3. Anyway, enough about that. Let's talk about cassava in general.